All right, here we go. You all see that?
Yep, looks good.
Excellent. Okay, so thanks. First of all, thanks for inviting me to to speak to the students. This is something that I always enjoy. I was telling Mr. Caldwell that now in my later years working at NASA, I enjoy sharing knowledge with students. And so I found it interesting that the American Society for Gravitational Space Research is an organization that I was not aware of. I always tell people it's always nice to learn something every day, and I was very impressed with what this society does, and I noticed that it's a lot with physical systems, living organisms, and I can tell you that from my presentation, you'll see that the living organisms, which are humans, in our case, astronauts, have a certain characteristic, capability, and let's say mannerism that as designers of systems that we take into space, we have to be aware of. And so my presentation is going to be covering hardware, software in developing these systems, but also the human element, which I found out in later years is just as critical and sometimes even more critical than the hardware and software. Interesting enough, the hardware and software is somewhat deterministic. You can design it, to do a specific task, if you will. Humans are not so deterministic. There's so many variables, and that's where you get into trouble. And when I say into trouble, that's when things like airplanes crash. That's when ships, like just about a couple of years ago, the USS McCain crashed into another Navy vessel and killed 5 people. Well, it turned out it was the interface of that vessel, of the USS McCain, that caused the shipwreck. And of course, you hear about planes crashing just about every year, and they call it human error, but in reality, it's the lack of the system to accommodate the human capability. And so in my presentation today, I'm going to be talking about the space environment at the high level and its effects on humans. I'm not going to get into all the details of it, but some of the key aspects that I'm familiar with that NASA's been researching and dealing with. Human error considerations is kind of give you a top view of, how do we consider the human error considerations in designing systems. And then the human machine design methodology. Here's where we get into, how does NASA design systems for human use in deep space missions? And I have to say that it's a little bit of complication associated with that. But I think it's also, this would be very beneficial for the student body, for the members of the society, to learn about this if they haven't learned already. A couple of areas I'll be talking about: systems engineering, and the other one is human systems integration. Systems engineering more so related to the hardware, software systems in the environment, and human systems integration actually goes beyond that. And I'll say more about that later in my presentation. And then a little bit of wrap up at the very end. I'll try to stay within time so I can have plenty of time for questions and answers. So first step is the space environment and the effects on humans. And what you're seeing here is some of the key physiological and psychological, let's call them factors that affect the human. And so you got the altered gravity physiological changes that are associated with, let's say, microgravity. Like right now, the orbiting space station is the astronauts experiencing the microgravity environment. When we go back to the moon, we're going to be experiencing 1/6 of the Earth's gravity. And of course, when we go to the moon, rather to Mars, it's going to be about 1/3 of the Earth's gravity. Still, it affects things like balancing disorder, fluid shifts. There's no sinus strain in the microgravity environment. Muscular atrophy. Your body actually grows a little bit when you're out in space, and primarily because there's no, the gravitational forces are much less, and therefore the body's responding appropriately. Hence, that's why you have calcium loss, because, and obviously the bone loss is because of the lack of calcium buildup. The body says, hey, there's no 1G gravity acting on me. I don't have to produce calcium for strong bones. And so your bones start becoming brittle and weak. And that's one of the reasons why they're doing some of the studies that they're doing for long duration missions is things like osteoporosis, which has very similar characteristics as far as bone loss. Space radiation, oh, that's a biggie. And it's not just for the humans, but also electronics as well. But for space radiation, obviously, it affects the immune system of the astronaut, obviously cancer, the cognitive abilities. Radiation can destroy brain cells and things of that sort. And once it starts destroying different pieces of the brain, your cognitive abilities start going down. Well, what happens when your cognitive abilities start going down? Your ability to control things manually using your eyes, ears, and what we call situational awareness deteriorate. And so there's where you're prone for an accident occurring. I'll say more about that later in my presentation. Isolation confinement, it's going to be a huge thing going to Mars. We're going to be millions of miles away from a rescue mission. So things like, from a standpoint of physiological, the sun right now, it provides circadian rhythms for humans here on Earth that maintains our sleep patterns. And when you start getting away from the sun, the characteristics of the sun in terms of the spectral characteristics, like for example the amount of blue light and the intensity of that blue light and things of that start deteriorating. And so that starts affecting the body and its ability to produce the necessary ingredients, if you will, in order for a human to maintain circadian rhythms. Isolation, that's a biggie. We're still not sure how well humans are going to behave when they go to the Mars. Obviously you hear about all these long-term studies here on Earth, and of course, the one that was done by Scott Kelly on the space station, I think it was about 5-6 years ago. He was the identical twin to Mark Kelly, and so he stayed up there for over a year. And of course, he had a lot of problems when he came back in terms of physiological problems and to some extent psychological problems. But the thing is that they were close to Earth, and so being close to Earth is actually something of a motivator, if you will. And I'm reminded of a Russian scientist that I met many years ago. And he told me that a lot of the studies they did in Siberia, that the test subjects said the only reason that they survived for so long being in isolation because they knew they were on Earth, and one day that door was going to open, and they were going to get out of there and go back to their family. And that's not the case when you go to Mars. So we still don't know how they're going to behave in that. And obviously, the behavior of a person that's depressed and physiologically and psychologically degraded, if you will, can affect how they operate systems. And of course, the hostile environment in terms of, need food, water, you're dealing with, CO2 levels in a confined environment, toxic exposure, the Mars soil is not very conducive for growing plants. It's a little bit toxic. So we got to alter that soil in order for that to happen. And of course, habitat is very important for the crew of for the care of the crew. If you want them to have plenty of room to do their work, you want it to be comfortable in terms of temperature and things of that sort. If not, it becomes a little bit of a disturbing environment for them to to do their job. Distance from Earth, there's going to be a case where there's medical emergencies, and how do we deal with that when they're so far away? It's a major challenge because a lot of the Earth's let's call it medical equipment, call them X-rays, MRIs, and things of that sort, are not suitable for the deep space environment, and therefore, how are we going to develop, let's say, compact systems that they can take into space, that can operate reliably in the space environment? That's another challenge. The other thing is associated with equipment, the considerations of the microgravity. There's no up or down in space. You can float around upside down, whatever, do spin. You can do spins easily and things of that sort. And therefore, labeling is important if you want to make sure the astronaut knows which orientation to be in to control a piece of equipment. And so the labeling up and down is important. Newton's third law must be considered. Here's a a case where you have to bring in a little bit of science. Newton's third law: for every action, there's equal and opposite reaction. And so when an astronaut is floating in space, sake of argument, that he or she presses a button, well, that button's going to push back on them. And so that's why astronauts, you'll see them before they get on the console, they'll put their feet on these little foot restraints before they start operating the system. So that way, when they start punching buttons or levers, that they don't go all the way back as they're operating the system. So microgravity environment and designing for that is very critical. Spacesuit glove and exterior limitations. The spacesuit is a very bulky, very hard system to be in and try to do your work. You know, a spacesuit roughly weighs about somewhere in the vicinity of 430 pounds. They usually pressurize it to 4.2 psi. And there's a reason for 4.2 psi rather than 14.7 psi, and that's because of flexibility. If you were to pressurize a suit to 14.7 psi, there's no way they could bend their arms or even close their hands. So 4.2 is the kind of the compromise. As a result, that's why they got to pre-breathe in order to be prepared for breathing the lower levels of oxygen that are associated with a spacesuit type environment. Health and safety of an astronaut is always considered in terms of equipment, whether it's in the microgravity environment on the moon as well as Mars. Is that safety and health is something that's always looked at in designing these kind of systems. Now, for speech control, it's going to be a little bit of challenging for that because of the acoustics associated with these kind of habitats and the psychological and physiological effects that must be considered. If you got an astronaut that he or she's not feeling well, depressed, they have a cold, things of that sort, their voice is going to change, and therefore the speech recognizer that thought it knew who was speaking is having trouble understanding that person. So it's a major challenge. Again, it goes back to the environment. And again, the environment is very critical as part of the holistic design of a system. Hardware, software, the human in the environment. All right, human error considerations. So let me just kind of briefly go through some of these. The first one is complex and difficult to use. You know, you got to trust the interface. If the system is very complicated and very hard to use, the astronaut is not sure how it's going to behave. There's a lot of errors because they got things wrong. They've lost trust in the interface. If you lose trust in the interface, the astronaut's not going to like it. And you know, we do some testing for that, and I'll mention that later on, having to do with workload and usability type testing. Along the same line is a heavy memory workload too as well. If you're requiring this astronaut to punch a bunch of levers and do a bunch of switching, it's going to affect their capability to remember a lot of things. You know, keep in mind that the human, unlike a machine, cannot remember a whole lot of things. And so I know as one gets older, you start remembering less and less. And so the memory workload is obviously critical as part of the design considerations and designing an interface. Inconsistency in the interface. When you got different spacecraft, you know, you're going from, let's say, the Orion spacecraft to a habitat on the moon to an EVA spacesuit to, let's say, a trainer on the ground. If each one of these has a different interface, well, guess what? You're going to have to remember how to operate each one of those different interfaces, and that puts a strain on the person. So you want consistency throughout all the interfaces. And sometimes it's a challenge because of the system capabilities, but that's part of the early evaluation of designs, making sure that there's consistency across the board through all the spacecraft. That's going to be a major challenge for NASA as we start going to the moon and beyond. Feedback ambiguity. If you're not getting the right feedback, you're not sure where you are in the system, and that's how sometimes accidents happen, is because of improper feedback from the system has occurred, and the person thinks that they're in this mode of operation when they're in that mode of operation, and they press the wrong button, and hence a hazard or some error has occurred. Labeling is very important too. Make sure you label things correctly. You don't want to label something that's dangerous with the green, let's say with green color, because green sometimes implies everything's good, where red implies danger. So you're going to be cautious about colors, cautious about your signs, what you say, and be consistent across multi-vehicles. Again, if we're going to be going back to the moon, and Mars, we're going to have different vehicles, and they're all going to have to be similar in order to minimize training. And then critical error prevention, I'll say more about that later in the slide that I have. And then the environment, I can't tell you how important the environment is. Layout, temperature, contamination, inducing effects. If you got a bad environment where these astronauts are going to operate in, it's going to be difficult for them to do their job. Down there at the bottom, I said that human error interface is basically defined as deficiencies in the interface that's a mismatch between the demand of the task and the human capabilities. And let me give you an example of that. On Soyuz 11, cosmonauts, and I forget, there were 3 of the cosmonauts, they died of asphyxiation. And so what happened when they brought them, when they came, when they returned to Earth, they thought everything was okay. You know, they landed properly, everything's hunky-dory, but when they knocked on the door, nobody answered. When they opened the hatch, they were all dead. It was completely depressurized. Well, what happened? Well, apparently a couple of things happened. And one of them was that a couple of rockets, retro rockets for jettisoning the command module from CERS module, fired simultaneously and caused a big jolt in the system, which basically caused one of the valves to shut inadvertently. Well, that valve was located under the seat of one of the cosmonauts. It was almost impossible to get to it. And then secondly, to turn that valve off, it took somewhere in the vicinity of 60 seconds to open up the valve. It took about 60 seconds to open up the valve. A human could do that in about little over 60 seconds. And so what happened was that valve was not designed for a human, to shut it off quickly for an emergency situation. So it's a case where the system was not designed for the human limitations. All right, so where do the errors and failures occur? Well, there's different areas here, and let's see if I can get my laser pointer here. Hopefully you can see that. So you got, here's with HSI, Human Systems Integration System View. Got the human, the hardware, the software, in the environment. And this is for total system capability. And so from the hardware, you have something called the bathtub curve. And this is something that happens with electronics and mechanical systems, is that early on, what's called the burning phase is usually associated with infant mortality. Stuff is new, we've produced it for the first time. And so you might have errors associated with production processes or things of that sort. And so you may have some pieces that'll break very early. But if everything goes correctly as designed, there's a phase called constant failure phase, whether it's mechanical or electrical, that basically you can compute the likelihood of an error occurring here because it's constant failure rate. But as you start going out into the wear out phase, all bets are off, if you will, because things start going non-linear. And so it becomes more difficult to find what's the likelihood of an error occurring. But that's why sometimes we'll design systems to have a minimal or maximum life, and sometimes this maximum life is a little bit less than what's anticipated for the hardware. So it's part of what we call derating analysis, which I guess another terminology is margin. How much margin do you have in your design? How much have you allocated for making sure that even when it's time to, let's say, decommission the hardware, that it still had a little bit of life left, but it's better to be error on the safe side. So software is a different beast altogether. It's not like hardware. Software, basically, you write a lot of software, you're going to have a lot of errors, but then as you start correcting the software, your errors go down, and then you get a minimum lambda, which is mean time to failure. But then if you're going to upgrade your software, well, guess what? You're going to have more errors, but then you basically burn down your errors, and then you keep doing it over and over, and that's where you got the sawtooth waveform. Eventually, you stop doing the upgrades. You basically corrected all the software, and now you have a constant failure rate. Now, for humans, it's a little bit different. And so, for the human aspect of it, you got these unsafe acts that can occur, and they're either unintended actions or intended actions. Unintended actions is you understand the system, but things didn't go right that day. And so sometimes the error types are flipped. Oh, I omitted something. The mistiming. I should have pressed this switch first and that switch, things of that sort. Or lapse in memory. Oh boy, I know the system, but today I couldn't remember I couldn't remember the sequence, or I couldn't remember what was first or what was second, things of that sort. So that's a lapse of memory. It's not that you don't know how to use the system. It's just that particular day, again, physiologically and psychologically, you just weren't all there, and so you made a mistake. And then there's this embedded. I was talking about mistakes. Actually, the mistakes are more associated with the system is new, and I'm learning it, but I'm going to make mistakes along the way because I don't know the system. Until I know it, I'm going to be erring quite a bit. And so it's rule-based mistakes. You try to apply a good rule, and sometimes the good rule becomes a bad rule. And so and then there's knowledge-based mistakes where you thought you knew how to use the system because of what's called your memory in terms of what you remember, how systems like this operate, and it just doesn't work out that way. And this one I hear violation is one that we usually don't consider for the most part. But let me say something about human error, because this is something that I have a great appreciation for. So there was a gentleman by the name of James Reason back in 1990 tried to figure out, well, why do we have all these hazards and events that that basically kill people? And what he found that when you're building systems, you want the system to be successful. We always tend to design for success, which can actually be a drawback at times. But when you design for success, you think about the barriers that help you design for success. So barriers are basically things that help you defend against a failure of a system. And so the barriers here, it's called the Swiss cheese model, and I made it a circular cheese. But the reason I did that was to represent this thing is all these circles are rotating. Requirements, you're building, you're designing, you're trying to design the best requirements. You're trying to design the best system. You're trying to factor in all the safety necessary, to ensure that the safety of the crew, safety of the hardware, safety of everything is possible. You want to do the best training possible, because you want to be successful, right? And then maintenance, you want to do the best maintenance, and then you want the crew to be perfect, and you pick the best crew possible. But guess what? None of this is 100% error free. We're human, and we're not perfect. We're gonna make mistakes in design. We're gonna make mistakes in requirements. We're gonna make mistakes in safety reviews. We're gonna make mistakes in training. And so these holes represent deficiencies or weaknesses in the barrier. And so you have here a representation of hazards that one particular hazard may occur that maybe you missed it in the requirement, you missed it in design, but safety caught it. You may have a hazard that went right through the requirement, through the design, through the safety, but training caught the potential hazard and corrected. But then there's that case, where things just lined up, they lined up properly. I want to say properly. All things lined up to create the accident. It just got through everything. And I'm reminded of the accident that happened in India. I think it was, I don't know, maybe 10, 15 years ago. Plant blew up, killed thousands of people. It turns out, if I recall correctly, there were 19 things that happened that accident to occur. It was just incredible, but it can happen. And so when you think about what ifs, when you're designing your systems, you design experiments if you're going to do something for Blue Origin, SpaceX, or NASA, there's I have to say, I call it the rule, the creed of an engineer is always be pessimistic. What if? What if this fails? What if that fails? Failure modes and effects analysis. You always want to think, what's the worst thing that can happen? What if, okay, everything is hunky-dory, but what if this fails? What if this valve doesn't close properly? Can it be open in time? Are there some limitations here that we're not aware of? And so you need to be thinking, I don't care if you're an engineer or a scientist, you got to be thinking about what ifs. If you're going to design an experiment, what if this goes wrong? And you always have to be thinking also about safety of an experiment, whether you're an engineer or scientist. So the safety aspects come into play. If you're going to train somebody to do the experiment, you got to think about training. Maintenance, if you got all this equipment that's necessary for doing the experiment, if none of that equipment has been maintained, well, what's going to happen to your experiment? So this is applicable in, I think, in any area. All right, so let's talk about situational awareness, and I'm just going to briefly cover this. So situational awareness is something that I came to learn became very important for human-machine design, particularly in the area of feedback. And so situational awareness is basically providing a awareness of your surroundings. And so it's made up of three parts: perception. Okay, what's happening right now? Where am I seeing right now? I'm seeing a wheel coming off my bicycle, or I'm seeing, I'm having to press my car brakes a little harder. Comprehension. I'm trying to comprehend, what does this mean? What is this? What I just saw right here? What is this? What am I trying to? What's this trying to tell me? I'm trying to comprehend, the situation, and then your reaction. Okay. So all these three, the perception, comprehension, reaction, is in contribution with your mental models. Mental models are basically how you perceive the world. All right. So if you have your certain mental models of how the systems you operate, and you have the situational awareness that combine those two together, you're going to make a decision, and then that decision, coupled with the interface design workload, will lead to your actions, and then your actions results, and then did you reach your goal or not? And so the goal feeds back to your current state of the environment, and of course the environment can be very dynamic. You got to keep in mind that humans don't just have one pair of eyes, one pair of hands, one pair of ears as well, one mouth, and limited attention and cognitive resources. So if you're designing a complex system, you really have to really think about whether we went overboard or not. And the only way to find that out is through testing and analysis. And so the contributing factors of situational awareness is, like, for example, facial. I thought I was here, but I'm over here, and I was, I'm disorientated. I should have been looking east instead of west, or things of that sort. And then you have system awareness, okay? Understanding the status of the system. What is the system trying to tell you? This is somewhat of a, comic and somewhat, but very true. Here it says, "Oh, the fuel light's on. Frank, we're going to all die. We're going to die," thinking they ran out of gas. And he goes, "Oh, never mind. It's an intercom light." Okay, so a misunderstanding of what that light meant. And so things like that is what gets you into trouble. So understanding the situational awareness of your system and what it's telling the user is critical, especially in safety critical or mission critical applications like NASA does, and federal aviation obviously as well, and the military as well. And so task awareness, competing tasks. People say I can multitask. Really, people cannot multitask. I can tell you that. I've seen many studies where people that think they can multitask, they find out that their ability to multitask degrades quite rapidly, especially as the tasks get more difficult. And so, and the demand of each task if this task, there's a high demand of tasks at different intervals of time, it can affect your cognitive abilities to be able to handle all those tasks. So this is, again, part of situational awareness, is understanding the environment. And there's a lot of dependency, especially if you got a human-machine interface, to make sure that information is provided back to the astronaut. And so let's now talk about the human-machine design methodology. And I'm not going to say a whole lot here. If you're familiar with a scientific method, which is basically make an observation, form a hypothesis, design an experiment, perform the experiment, gather the data, and compare it against your hypothesis and decide, if it's right or wrong. This is basically what systems engineering is all about. Let's call it the systems engineering equivalent of scientific method. You're defining the requirements on the left-hand side, and this is happening in different phases of a project. Okay, this is the cycle phase of you get into the concept development, preliminary design, final design, assembly of the system, and then launching. Okay, but it takes processes along the way. And so in order to do that, you got to have a methodology for doing that. Systems engineering does that. If you first do the system design process, like defining requirements, and then developing a system based on those requirements, and developing a prototype and see, is this the correct system or not? Again, you design just like you design an experiment, like your hypothesis. And then if it is, then you go into the integration and testing of a system, and that's part of the product realization process. In the middle is where there's a lot of activity going on. The planning process, the requirements management, interface management. I'm interfacing to different systems. How does my system affect others? How do others affect my system? Technical risk management. That's a huge thing. What are my risks of the project? What are the risks in terms of schedule, costs, and technical? And then assessment. Oh my God, technical assessment are happening all the time, and decision analysis. And so, but there's also scoping, and early on you're scoping the project to see if it's even doable. So you're looking at, what are the objectives? What's the mission? What are my assumptions, constraints, responsibility, authority? You may find out that this experiment that you're trying to build is not feasible, and you stop right there and you don't go any further. And that's actually a good thing, because you're wasting time and money if that's not the case. And so you're doing definition and composition on the left-hand side, and integration and verification and validation on the right-hand side. Two differences between verification and validation, or the difference rather. Verification says, did I build the system correctly and according to specifications? Validation is even more important. Did I build the right system? And so all along the way, you're developing the requirements, you're maintaining the system. As you're changing it, you're controlling it, you're verifying it, and you're validating it. Along the way, you're doing also human systems integration. And human system integration is basically, and I won't get into the details of this, but basically it's ensuring that you're factoring the human element throughout the life cycle of developing the system. So the technical process of the human systems integration is ensuring that the human performance has been factored into the system. Recall the Soyuz 11 tragedy. And then there's the technical management aspects of it, ensuring that all phases and all aspects of the development, if you look at the systems engineering cycle, that the human element is always being considered. And what you're trying to do ultimately is that you're trying to maximize performance, reduce the cost, and reduce the risk. That's basically it. It just takes a lot of processes in place and a lot of iterations. That's what these arrows mean in order for that to happen. And for the design considerations of safety, you got to think about space application safety, seeing the displays, the color, the font size, glaring, how does that affect caution and warning messages? Auditorial, okay, environmental noise, reverb, echo effects can affect hearing things in the space environment. Tactile feedback is critical. Electromechanical versus touch switches. You saw at the beginning of my presentation, it was a picture of the SpaceX touchscreens. And a lot of people think they're cool and the latest technology. Well, I can tell you because I've been involved in that project, it was not trivial to make those guys work. And also, by the way, those touchscreens are not used for critical applications. It's for non-critical applications. So you got to be thinking about that. Switch cards. You don't want to switch to be into a position inadvertently because you kicked it. Keep in mind if you're in the microgravity environment, you're floating around. You can actually, you could kick a switch into an on position. Not a good thing, especially if that switch fires a rocket when it's not supposed to. Man activation, must work functions. I mean, these are functions that have to work 100% of the time. And then function grouping, in other words, you put all your if you got a panel, you put all your, let's say, life support system switches here, all your power switches here, all your reaction control rocket systems here. So they all are categorized, if you will, and that way there's less likelihood of making a mistake. Status lights, status of the switch, or is it the status of the system? You need to make sure that the person understands that the status of the switch is much different than the status of the system. And then design for environment. Here's where it gets very expensive. Here's where you're testing temperature, vibration, electromagnetic compatibility, humidity, shock, radiation, dealing with the gravity effects. All this is important because you can have a system that does everything it's supposed to do functionally, but if it cannot survive in that environment, it starts to misbehave. When it starts to misbehave, you got a failed system. And then if you compound that with a deficient human interface design, for example, feedback, and the astronaut doesn't know how the system, what state is in, and things of that sort, even more trouble for the astronaut, and even more trouble for the system. And then some key engineering activities. I won't say too much about this, but basically, you're developing requirements. You're developing the concept of how the system is going to operate, the behavior of the system. You're developing the physical of the system. I'll say more about that in the presentation. You're evaluating and optimizing the design solution, and you're doing an assessment, and you're doing decision analysis. And this is part of what's called human-centered design. In other words, the human is always factored into all those aspects of that process. And that takes you to preliminary design. You're saying, hey, we finally found a system that's going to work. And at that point, the powers to be or the project manager says, okay, it looks good. We're going to give you more money. Now you go to critical design review, and now we want you to build the final system that's going to fly. And of course, on the right-hand side is where there's all the testing that goes on, the component testing, like vibration testing, electromagnetic testing, and then what we call run for the record human in the loop test. In other words, did the system do what it's supposed to do? You're validating the system. And of course, there's a lot of processes involved from the management aspect, ensuring that this is happening. Because now you're coming down to the wire right here, and it's kind of like the last stretch of the 1 mile run, and so you got to make sure things are happening correctly and they're happening at the appropriate time. So you got first, you got the requirements, you got the behavior architecture and the physical components. The requirements is the behavior of the architecture, and think of this as software for the most part. And then its interaction is allocated to components. Okay, who's going to do what? Who's going to do the switching of the rockets? Who's going to do the switching of the displays? Is it the human or is it a autonomous system? And so the physical system components, the behavior, you're checking that, and then the behavior is all based on a requirement. So this is kind of a process, that you're verifying all aspects of the development cycle. And you're looking at tasks, what tasks are going to be done. There's an example of all the tasks that may need to be done, but how well do they need to be done? And then the use cases, time sequence diagrams, state diagrams. How is the system supposed to operate? This information is vital and necessary for creating the software, things like state machines that basically tell you, how system is supposed to transition from one state to another is critical in the software. This is an architecture notional of a human-machine interface, and you got a physical layer, which is basically the physical components like displays, buttons, and things of that sort. And then you got the machine. It could be a robot. It could be camera systems. It could be just about anything. As long as it's a mechanical system of some sort. And there's a physical interface that's the interface to the user interface that basically is communicating, that provides the information back to the user. But that's just not all of it. Then the behavior, here's where the critical part is, okay? It's the display presentation of the information. You got the control interface, the dialogue. Dialogue is absolutely the most critical part of this. How are you interacting with a system? If the system is not doing what you think, again, your mental models is not doing what you think it's supposed to be doing, your display presentation could be inadvertently causing the user to hit the wrong switches. And then you have task aids, like, for example, electronic procedures that you can refer to, or maybe you can get into autonomous mode where it does everything for you, and you just sit back and watch it do its thing, if you will. And then there's the optimization, and I'm not going to get too much into this for the sake of time, but just basically, you're developing requirements, the task, you're doing analysis as you're developing the design, and then you're kind of feeding this back to the requirements. Are we getting the right requirements? Are we developing the concept? If we're doing this correctly, let's take it another step. Let's prototype the system, let's evaluate it, and then let's evaluate it in terms of usability and workload, effectiveness, efficiency, satisfaction. And we're looking at all this in a continuous fashion, feeding it back to the human analysis, and seeing if the design is correct. Okay, it's a constant loop, if you will, that's happening over and over again. But that's the only way you can optimize your system in terms of coming up with the system that you need that basically performs the mission, performs the task, and with minimal error, and that's important. And so, as a wrap up, understanding human-computer interface for space requires many aspects. You got the human factors engineering, human systems integration. You got to factor the environment. You got to factor the safety, the electrical design as well, and software design, certainly. Most designers understand hardware and software, not humans. I can tell you that in school, I was a double E undergrad, and I have to say that the only class I took about anything related to the human was my bowling class, because I was on a bowling team, and that was the extent of my human element aspects of undergrad. And then we're going to have new human-machine interface territory for future NASA space missions. I can tell you that one of the major call it risk and gaps for deep space exploration, according to the Human Research Program at NASA, is lack of good human-machine interface design. So that is a major challenge, and that's the area that I'm currently working to. So I'm very thankful for being involved with this kind of system design, if you will. And that concludes my presentation. Let me stop the screen, and let's go to questions.
Awesome. Thank you so much. That was really, really interesting. So we have a lot of questions today. So just in the interest of time, I'll just do a selection of questions. I'll try to make sure that everyone who asked a question gets at least one of their questions answered. So first, I'll start with a couple of questions that were from the registration link that people asked before today started. And the first one says, autonomous space systems, humans on the loop, in the loop, or out of the loop? I'm guessing that refers to like where humans would be situated within these systems.
For autonomous systems? Okay, so for autonomous systems, I think for space applications, we're going to have a system that is, let's call it semi-autonomous, because it's in autonomous mode, but the human is aware of what the system is doing, and at any time he or she can intervene and take over the controls. Case in point, Apollo 11 Neil Armstrong was getting ready to land. That system was on autonomous mode to land the Tranquility, see, yeah, the Eagle. I'm sorry, the Eagle. It was supposed to land the Eagle on the moon. Well, Neil looked out the window and said, "Man, we're going to land on a bunch of rocks. We're going to crash." And so, he took over control. He disabled the autonomous system and took over the rotational and translational hand controllers and found a spot with a little bit of gas to spare and landed correctly. So it's we got to be cautious about autonomous systems. Of course, you've heard about Tesla, where cars have crashed because of this being in autonomous mode, and people, whether they failed to understand what the system was doing, or were not able to react fast enough in order to take over the system. So I can't say there's going to be a full autonomous mode. There's some things that you just can't get away from as far as autonomy. Like, for example, during the launch phase, and this is something Warner Brown was very adamant, that the computers were going to control the launch system because there's so many things happening dynamically as the vehicle is going uphill, as they call it. And so a human cannot respond fast enough to control a rocket going that fast, through that dynamic environment. And so there was an autonomous aspect to the vehicle, but of course they also had the option, if things are going bad, to hit the abort button and get the heck out of there. So, and then certainly there'll be some things that'll be autonomous, but they have to be weighed on a case-by-case basis in terms of criticality and in terms of how necessary it is for the human to be aware of the system. We just cannot solely rely on an autonomous system that's been tested adequately on Earth, but yet you can't always rule out that Murphy's Law is operating 24/7. And so you got to have a backup plan. And that's, going back to the what if scenarios, right? So what if this autonomous system fails? Shut it off and go to manual mode.
Great, thank you. The next question is, what is your advice to worldwide aerospace students in order for them to reach their goals?
I'm sorry, can you repeat that?
Yeah, absolutely. What is your advice to worldwide aerospace students in order for them to reach their goals?
To overcome hurdles?
To reach their goals.
I'm sorry, to what now?
To reach their goals.
To reach goals? I guess, okay, to reach their goals. So just to make sure, what's my advice to students to reach their goals? Well, I mean, this is another story that I could share you with. You're going to suffer setbacks, and people say I failed here, I failed the test, I failed. I always have this issue about test taking. I wasn't a very good. Let me say, I was not a very good test taker at the university, and so you're going to have some setbacks, but you cannot say I failed. It's a setback, and eventually you're going to get there. It's just a matter of how much perseverance you have, and perseverance is not measured by any tests. It's not measured by any anything that I'm aware of. That it's up to you. It's in your heart. How bad do you want it? I wanted bad to graduate, and so I hung on for dear life and was able to graduate. And I was able to also secure some good side jobs, if you will, while I was going to school. Actually, that helped me get into NASA, not necessarily my GPA. So, sometimes it's not, what you, accomplish, whether it's, it could be a low GPA or a high GPA, but it's what you do with that. And that's the important thing. So, the success is really dictated by, you as to, how far you want to go. But it's possible. And so, to me, the number one ingredient is perseverance and hard work.
Awesome. The next question is, there are actually a lot of questions about automation, so I'll just go with this one for now. Does the increase in the level of automation, including machine learning and artificial intelligence, change the focus, activities, or priorities in the HSI process? If the machines are getting more complex, does the HSI process need to get more complex as well?
I think so. One of the things that we are still struggling with, and I'm talking to some of my colleagues in the human factors area, is devising testing methods, for autonomous systems. That's something that's kind of new to us to some extent, but it's not obviously, insurmountable that it cannot be done. It's just a matter of, determining how we're going to verify an autonomous system that changes because of AI and machine learning. Okay, so if these systems are learning in space, well, how are you going to deal with a system that you just verified on the ground with this certain machine learning algorithm, if you will, but now it's changed as you go deeper into space? Well, how are we going to validate or verify that this system in real time is good, if you will? And of course, JPL has done this to some extent, with their Perseverance and Mars Science Laboratory. But when you consider the human in there, it changes the equation a little bit, and that's something that I've been discussing with some of my colleagues in terms of what's called the digital twin. So digital twin stems from what the automation industry, or rather automobile industry, as well as oil and gas is doing, is where they basically have a model of the system, and they're getting data back from the actual system, and they're comparing the model from they're comparing the model against the actual data system. And so I envision that in the future, the NASA is going to have some kind of model of the human and the machine and the autonomous all operating collaboratively together. But then the real data is going to be coming back from from the actual mission, and then we're going to be updating our models in order to change things. Nothing new. We did that on Apollo 13 when the Apollo 13 was crippled, and they did they were looking at the data coming back from the power grid, if you will, of the Apollo 11 service module and command module, and then they started to simulate on the ground those kind of scenarios, and that's how they came up with a way of basically helping the astronauts can come back with minimal power. So it's an example of having a digital twin in place, and that's what I foresee for our future missions. So it is a challenge in terms of the amount of data required for that, because we cannot transmit a whole lot of data right now in deep space, and there are some limitations associated with the radiation effects on some of the electronics that are needed for doing some very high speed stuff. But we're getting there. It's just going to take a while.
Great. The next question, and probably the last question for today, is do you have specific methods to evaluate the astronauts' level of trust in automation?
Do I have specific methods to evaluating the trust? Okay, so trust is it's kind of a terminology that kind of factors in different aspects of it. One of them is certainly the reliability of the system. Okay. And so, you have to think about the reliability, you got to think about the usability, you got to think about the workload. And so right now, I mean, at least on the books per se, NASA doesn't have what you call let's call it a trust test, if you will. Okay. It's kind of, I think right now, separated out into different pieces. If we were to look at something called, the trust factor, it would actually be a combination of many things. That would be the usability of the system. How easy, how user-friendly is it? How efficient is it? How effective is it? Does it require a lot of memory retention and recall in order to operate? Workload, how much workload does it take? And then how reliable is it? Does this thing keep breaking down so many times? I can tell you from experience, many years ago, when we were doing some early speech recognition work on shuttle, there was one group of folks, and I'm not going to name who they were, that they were developing a system for a shuttle experiment, but the physical hardware components were failing. And so the astronauts' philosophy of speech recognition, even though it was not the speech recognition itself, but it was the hardware, the philosophy was the speech recognition is terrible technology. See? So, you got to be cautious about that, because you can put a stigma on certain technology. And so, some of the things we're going to have to factor in as we start using or getting into new technology, like in situ resource utilization, or more advanced cryogenic systems that we're going to need for deep space. So we're going to have to be cautious in how we develop those systems, making sure that they're reliable. And going back to the interfaces, we're going to be using interfaces with autonomous systems, with AI, with machine learning, is making sure that they're reliable. And so how do we build that trust? Well, we build that trust through letting them know that, hey, this stuff is not going to fail on you when you need it the most, and from a hardware point and from a software standpoint. So right now we don't have an official trust mechanism in place right now, but we do have elements that collectively come together to build that trust for the astronauts to use the system.
Awesome. Well, thank you so much. Looks like we're coming up on the hour. So I just wanted to say thank you very much for taking the time out of your day to give us this really awesome presentation. And thank you everyone for coming today.
Thanks for inviting me.
Thank you very much for coming today, George. It has been a real pleasure.
Thank you.